Hi, my name is Evia. I am from Ridgefield High School, and this is my presentation on the short-term pilot biodegradation analysis of pathema, polymer methacrylate, and PMMA synthesized in supercritical carbon dioxide. So first I wanted to go over a little bit about polymers. There's some main issues with polymers, and that is that 99% of man-made polymers are non-renewable, which means they're made from resources such as fossil fuels. Furthermore, polymers, a lot of them biodegrade very inefficiently since they're built to last rather than be used once and thrown away, which many of them are. In order to create better plastics, it's important that the plastics are renewable and biodegradable. One big issue is that a lot of plastics are marketed as environmentally friendly when in fact they are either renewable or biodegradable. So in order to create better plastics, they should be both renewable and biodegradable, and they should also be similar to conventional plastics. This means that they should be similar in structure, and they should have similar uses and be able to be used in similar ways as normal plastics are. And in addition, renewable plastics and biodegradable plastics should be easy to manufacture because a lower manufacturing cost means they can be sold at a lower price and are more marketable to consumers. One potential solution for this is terpenes, and terpenes are bio-based, which means they're renewable molecules, and they can be obtained from plant waste, such as from orange peels and trees. They're also easily modifiable, and this means they can be used in a lot of different ways as monomers for plastics that are renewable, and they're cheap, which is really important to pricing the plastics at a sustainable rate. I quickly wanted to go over some literature that I read and took notes on over the past 2 years. First of which being biodegradation of a variety of bisphenols under aerobic and anaerobic conditions. And this article taught me a lot about how plastics biodegrade in different conditions, such as ones with air and without air. This funneled me into the article Life Cycle Analysis of Extruded Films. And here I learned a lot more about the entire life cycle of a plastic and the environmental damage it does from start to finish. It goes as far back as like what the environmental damage from the land used to create products that are used to create the plastic, to the biodegradation of the plastic or the other methods of disposal. This funneled me into the article of facile and green roots of terpene-derived acrylate and methacrylate monomers. And here I was able to connect to my mentor who was able to send me samples of the plastics I'm using. And I also learned more about these plastics that I was very interested in, which are renewable but not have been studied for biodegradation yet. This funneled me into my last article, Biodegradability of Plastics Testing, which is the basis of my methodology. Some quick going over my contacts. I contacted Dr. Noyes, who is a former RHS science teacher, which is my high school, and he gave me a lot of advice with my methodology, and he gave me outside info, such as new perspectives with microplastics and different ways to look at the biodegradation of plastics. I also reached out to Dr. Teresco, who I mentioned I connected to through that journal article, and he was able to give me the plastic samples that I would like to use, and which are renewable plastic samples, and he studies material science at the University of Nottingham. I also reached out to Dr. Biardi, who provided me space at the Environmental Science Laboratory at Fairfield University to conduct my experiment, and he gave me some key details with my procedure. So to sum up my hypothesis, I hypothesized that to replace a conventional non-renewable plastic, the renewable replacement should have similar structural properties to the non-renewable plastic and should have a similar or faster biodegradation rate in order to create less environmental damage overall. The plastics I'm studying are pathema, polymer methacrylate, and PMMA. Both pathema and polymer methacrylate are renewable plastics, and PMMA is not. In fact, you might know PMMA because it is commonly known as acrylic or plexiglass, which I might be referring to it as that way throughout the presentation. So what's actually going on in my experiment? I analyzed 6 samples of plastic, 2 samples of pathema, 2 samples of polymer methacrylate, and 1 sample of acrylic, and then my control sample was soil only and no plastics. So the temperature and time you see next to each plastic sample, when these plastics were synthesized, because they use supercritical carbon dioxide, a powder was created, not the actual film. So in order to create that film, the plastics needed to be melt pressed, and this required them being heated up to a certain temperature, which is listed next to each plastic sample, and then pressed for a certain amount of time. So in order to conduct my experiment on the biodegradation of these different plastic samples, I put each sample in a jar and left it to biodegrade for 10 weeks. Each jar, as you can see on the right, has water, a certain amount of 1 plastic sample, and a solution of potassium hydroxide. So the potassium hydroxide is important, and it's the main component of how I'm measuring the biodegradation because I'm using a titration in order to identify how much carbon evolved from the plastics. So during the biodegradation process, essentially what happens is microbes will eat the plastic, and then as a byproduct, they'll release carbon dioxide. And the carbon dioxide contains carbon that came directly from the plastic. So the carbon dioxide will find its way into the potassium hydroxide solution because the jar is a closed environment. It's sealed and there's no air getting in. So once that carbon dioxide finds its way into the potassium hydroxide solution, the potassium hydroxide becomes a mixture of potassium hydroxide and potassium carbonate of an unknown concentration. So I used hydrochloric acid and phenolphthalein to titrate the solution and figure out how much of the solution was potassium hydroxide and how much was potassium carbonate. Here's my raw data. It's a bit messy. However, the main thing I wanted to point out here, this is the graph of how much hydrochloric acid I needed to titrate the solutions in each of the jars to the equivalence point. And the main thing I wanted to point out is that there is evidence of biodegradation occurring, because if there wasn't, all of the lines here would look like the black line. Since each line is each jar, and each jar contains a different plastic sample, if there's no biodegradation, then all of the jars would be releasing the same amount of carbon, and therefore they'd all look the same. However, they don't, so there's evidence of biodegradation. After doing some calculations, I ended up with this graph, which is the total amount of carbon that evolved from each of the jars. I used the black line, which is the soil-only control sample, as my baseline for this graph, because there's a certain amount of carbon that's just going to come from the soil naturally, and then there's also a certain amount of carbon that's going to come from the plastics. So using the control as my baseline, this is the amount of carbon that comes from each plastic relative to how much just comes out of the soil baseline. So there seems to be evidence of biodegradation, especially in the light blue line, which is PAPIMA. And there's also a margin of error that I need to point out here. And that is because there's variability in my experiment due to the lack of replication I used. I only did one jar of each sample. So because you can't exactly have a negative amount of carbon evolving from a jar, it can be assumed that the negative values here are variable amounts of carbon that evolved from the soil rather than amounts of carbon that evolved from the plastic. So the main thing with this graph, as I mentioned, is that there's more evidence of biodegradation. The most evidence of biodegradation is in the PAPIMA sample, highlighted in blue. Another important thing is that there's fungi growth at week 8 in my experiment. You could see it in the jars. It was filamentous. And as you can see in my data at week 8 and above, there's a decrease in the amount of carbon produced from the jars relative to the control sample. And this shows that there could be potential variability in my results resulting from the fungi growth. So if we shorten the amount of time this experiment went and remove weeks 8 and onward of my data, then you can see there's clear trends in biodegradation here. The PAPIMA samples, which are the dark blue and the light blue samples, show clear trends of biodegradation since they're above the line of the soil-only sample, and also plexiglass, which is the red line, shows biodegradation. However, both samples of polymer methacrylate do not show any signs of biodegradation, which means that there's a potential that something happened during the melt pressing process that strengthened the structure of the plastic. So when the plastics were melt pressed, there's a possibility that they're cross-linked, and that would strengthen the structure of the plastics and lead to a slower rate of biodegradation. Furthermore, as I mentioned, there's no replicates of any of the samples used, so there's a lot of variability that could potentially be occurring in these results. However, these are promising pilot results, and with further studies that could be conducted, we could potentially see that PAPIMA could be a potential replacement for acrylic, since PAPIMA has a very similar structure to acrylic, and it has very similar uses and is as strong as acrylic, and it could potentially have a faster biodegradation rate than acrylic, and it also is renewable, which acrylic is not. Thank you so much for listening. My name is Evia Rodriguez. I'm from Ridgefield High School. My contact info is on the board, and I'd be happy to entertain any questions.